Hello dear students, this is Tamás Jávor. Welcome back to Rubber Duck Physics. Today we are going to revisit some key concepts from circular motion. We'll cover angular displacement, angular velocity, and a few related quantities. These are essential for understanding how objects rotate, but don't worry, we'll break everything down step by step. Let's start with angular position. If we have an object moving along a circular path, like our rubber duck swimming around a circular pond, we can describe its location using angular position, denoted by the symbol theta. This is the angle between a reference direction, usually the positive x-axis, and the position of the object along the circle. The unit we measure angular position in, remember from the previous video and say it out aloud with me, radians. Yes. As our rubber duck swims around, the angular position, theta, changes. The difference between the starting position and where it is now is called the angular displacement, delta theta. Just like linear displacement is the change in position along a straight path, angular displacement, delta theta, is the change in angular position, theta, as an object rotates. Angular displacement tells us not only how much an object has rotated, what angle, but also in which direction. Imagine our rubber duck swimming around the pond. If it swims counterclockwise, we call that a positive angular displacement. And if it swims clockwise, that's a negative angular displacement. And just like in real life, the duck can swim around the pond more than once. So angular displacement can be greater than 2 pi radians when the object makes more than one full loop. Or it can be more negative than -2 radians if it swims the other way. Now let's talk about angular velocity, omega. Angular velocity tells us how fast something is rotating, and is defined as the rate of change of angular displacement. So angular velocity is the angular displacement, delta theta, divided by the time interval, delta t. In simple terms, it tells us how fast an object is spinning. You can easily derive its unit. The angular displacement is measured in radians, which is dimensionally just 1. The time interval is measured in seconds. Therefore, we express angular velocities in 1 per second, having in mind that it means radians per second. Just like with displacement, angular velocity can be positive or negative, depending on the direction of rotation. If the duck swims counterclockwise, we call it positive angular velocity. If it swims clockwise, it's negative angular velocity. We also have the concept of angular speed. This is simply the magnitude of angular velocity. It's how fast something is rotating, but without considering the direction. So whether an object is rotating clockwise or counterclockwise, the angular speed will always be positive. However, in physics, we focus more on angular velocity because knowing the direction of the rotation is just as important as knowing how fast something is spinning. So you won't need to use angular speed very often in this course, but it's good to know the difference. Now let's introduce the time period, t, and frequency, f. The time period, capital T, is the amount of time it takes for one complete rotation, and the frequency is how many full rotations happen in 1 second. Imagine a merry-go-round. If it takes 3 seconds to complete one full turn, that's the time period. But if it speeds up and completes 2 full turns in those same 3 seconds, its frequency has increased. So, while the time period tells us how long one full turn takes, so it is measured in seconds, the frequency tells us how many turns happen in 1 second, therefore it is measured in 1/second. In the areas of oscillations and waves, this same unit gets a name, but in case of circular motion and rotation, it is common to leave it 1/second, or rotations per second. You may sometimes see it as RPS. Notice that this time we are talking about the real number of something in a unit time. Therefore, it is not radians per second, but 1 per second. Time period, frequency, and angular velocity are all descriptors of circular and rotational motion in time. Therefore, let's see how they are interrelated and can be calculated from each other. For that, first, consider one whole circle turned uniformly. You can very easily see the values of the basic quantities describing this completed motion. Substitute into the definitions of frequency and angular velocity, and you will get all the 6 equations relating the quantities to each other. To accept that these are true for other angles turned than a whole circle, it's enough to consider that the number of revolutions, including even if it's not a whole number, the time passed, and the angular displacement all change proportionally to each other. Now let's connect angular velocity of an object moving in a circle to its linear velocity, which in this case we can also call tangential velocity, because its direction is always to the tangent of the circle. The two are related by this formula, v equals omega times r, where r stands for the radius of the circular path. This formula tells us that for a given angular velocity, omega, the linear velocity v increases as you move farther from the center of rotation. That's because objects which cover angles at equal rates but are farther from the center of the circle cover more distance in the same amount of time. Imagine a spinning bicycle wheel. The tire at the edge of the wheel moves faster than a point at the middle of the spoke, and the point on the rim of the hub at the center moves even slower, although they of course must rotate together. All 3 parts have the same angular velocity, but because the tire is the farthest from the center, it has the highest linear velocity. Let's show that the 2 sides of the equation are dimensionally equal. You multiply 1/second, where you know 1 is for radians, by meters to get meters per second. Then think about the following. So far, we have talked about how a point mass, like our rubber duck, moves in a uniform circular motion around the circular path. But what if we placed our duck on a rotating disk? Now, instead of just moving along the circle, the entire disk rotates. In the next video, we'll explore how rotational motion works for extended objects, like this rotating disk, and see how it relates to the circular motion we have been discussing. So, today we have covered the basics of angular displacement, angular velocity, and how time period and frequency fit into the bigger picture. In our next video, we'll dive into the exciting world of rotational motion. Thanks for watching! If you are looking for more personalized help with your physics studies, whether it's DP physics, A-level physics or math, or AP physics, I am available for online tutoring. You can find my contact details in the description of the Rubber Duck Physics YouTube channel. Make sure to check it out on a web browser. Feel free to reach out if you would like to book a lesson. Thank you for watching the video. See you next time.